Welcome back to G Fun Facts Online. Today we are journeying into the absolute center of our galaxy to confront a mystery that challenges the very foundations of modern astrophysics. For decades, the scientific community has held a consensus about what lies at the heart of the Milky Way. We look some 26,000 light-years away, through the thick obscuring curtains of interstellar dust and gas in the constellation Sagittarius, and we see a frenetic dance. We see stars whipping around an invisible point at terrified speeds, anchored by a gravitational tyrant we call Sagittarius A. We have crowned this tyrant a supermassive black hole, a singularity of infinite density and zero volume, from whose event horizon not even light can escape. It is the monster in the dark, the engine of galactic evolution. But today, we are going to explore a radical, unsettling, and incredibly elegant hypothesis that suggests we might be wrong. In the quiet corridors of theoretical astrophysics, a new theory has taken shape, suggesting that the monster is not a hole in reality, but a beating heart of dense, exotic matter. This is the story of the Fermionic Heart hypothesis, a theory proposing that Sagittarius A is not a singularity, but a dense ball of dark matter particles known as darkinos, held up against the crush of gravity not by an event horizon, but by the fundamental laws of quantum mechanics. If true, this rewrites the history of our galaxy and solves the mystery of dark matter in one stroke. To understand this revolution, we must first understand the regime it seeks to overthrow. The story of Sagittarius A is one of the great triumphs of 20th century astronomy. The center of our galaxy is hidden behind a smog of dust that visible light cannot penetrate. To see it, astronomers have to look in the infrared and radio wavelengths. It started in the 1930s with Carl Jansky detecting radio waves, but it wasn't until the late 20th century that technology allowed us to zoom in. What astronomers found was baffling. They saw a compact radio source, bright and violent. But the true revelation came from watching the neighbors. A group of young, massive stars, known as the S-stars, were observed orbiting this invisible point. The most famous of these is a star named S2. S2 became the Rosetta Stone of the galactic center. Over the course of a 16-year orbit, S2 swings perilously close to the center, accelerating to speeds of over 17 million miles per hour, which is about 2.5% the speed of light. By tracking this orbit with extreme precision, using the Very Large Telescope and Keck Observatory, two independent teams, led by Nobel laureates Reinhard Genzel and Andrea Ghez, calculated the mass required to whip a star around so violently. The result was inescapable. 4 million solar masses were crammed into a space no larger than our solar system. In the standard model of physics, only one object can possess such density without collapsing, and that is a black hole. This discovery earned Genzel and Ghez the 2020 Nobel Prize in Physics. The case seemed closed. We had weighed the ghost, and it was a heavy one. Then, in 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A. It showed a glowing donut-like ring of superheated plasma surrounding a central region of darkness, which was interpreted as the shadow of the black hole. To the world, this was the final confirmation. We were looking at the event horizon, the point of no return. But science is rarely about finality. It is about the nagging details that do not fit. The black hole hypothesis, for all its success, has cracks. The first major crack is the mystery of the G2 cloud. In 2011, astronomers discovered a gas cloud named G2 on a collision course with the galactic center. The physics of black holes are brutal. As a gas cloud approaches the event horizon, tidal forces should stretch it into a long, thin noodle, in a process literally called spaghettification. Astronomers prepared for fireworks. They expected G2 to be torn apart, causing a massive flare of X-rays as the material fell into the black hole. In 2014, G2 made its closest approach, and nothing happened. The cloud survived. It stayed compact. It swung past the monster and continued on its orbit, largely unharmed. A black hole should have shredded it. Why did G2 survive? Proponents of the black hole theory scrambled for explanations, suggesting perhaps G2 was not a gas cloud but a star hidden inside a dusty shell. But the Fermionic Heart theory offers a much simpler explanation. It suggests G2 was not torn apart because there is no singularity. The gravitational pull it experienced was from a fluffy ball of dark matter, which has a much gentler gravitational gradient than a point source singularity. Beyond this local anomaly, there is a deeper cosmological issue known as the origin problem. We see supermassive black holes, billions of solar masses in size, existing in the very early universe, just a few 100 million years after the Big Bang. In the standard model, black holes grow by eating matter. But to get that big, that fast, they would have to eat faster than the laws of physics allow, exceeding the Eddington limit. There simply was not enough time in the early universe for black holes to grow from stellar seeds to galactic monsters. This timing problem suggests that the seeds of these giants were not small black holes, but something else entirely, something that was born heavy. This brings us to the core of the new theory. Enter the International Center for Relativistic Astrophysics and a team of researchers including Carlos Arguelles, Valentina Crespi, and Remo Ruffini. They proposed a daring alternative. What if the center of the galaxy is not empty space, but full of darkinos? To understand their theory, we must look at quantum mechanics. Particles in the universe are divided into two camps. You have bosons, like photons, which can pile on top of each other indefinitely. And then you have fermions, like electrons, protons, and neutrinos. Fermions are antisocial. According to the Pauli exclusion principle, no two fermions can occupy the exact same quantum state at the same time. If you try to squeeze a lot of fermions into a small box, they push back. This quantum pressure, also called degeneracy pressure, is what keeps white dwarf stars from collapsing under their own gravity. The Fermionic Heart hypothesis suggests that dark matter is composed of a new, light fermion species dubbed the darkino. These particles are neutral, meaning they do not interact with light, and they are relatively light, in the range of 50 to 350 kilo-electron-volts, making them much lighter than an electron. Because darkinos are fermions, they cannot be crushed into a singularity. If you pile enough of them together in the center of a galaxy, their quantum pressure fights back against gravity. Instead of collapsing into a black hole, which is a point of infinite density, they form a dense, stable core. This core would look, from a distance, exactly like a black hole. It would have the same mass, 4 million suns. It would be incredibly compact. But crucially, it would not have an event horizon. It would have a surface, or rather, a fuzzy edge where the density drops off. It would be a solid ball of dark matter, a fermionic heart. The beauty of the Fermionic Heart model is that it does not just explain the center, it explains the whole galaxy. This leads us to the core halo solution. Standard cold dark matter simulations predict that galaxies should have a sharp spike, or cusp, of dark matter density right at the center. But observations often show a core, a flat, constant density region. This disagreement is one of the biggest headaches in modern cosmology, known as the core-cusp problem. The darkino theory solves this naturally. The quantum pressure of the fermions prevents them from piling up into a sharp cusp. They naturally settle into a flat, dense core. In the standard picture, we need two separate things to explain the Milky Way. We need a supermassive black hole to explain the center, and a separate dark matter halo to explain why the outer stars orbit so fast. These are usually treated as two different entities. The fermionic model unifies them into a core halo distribution. In the center, the density of darkinos is high enough that quantum pressure dominates. This creates the compact object that mimics Sagittarius A star. As you move outward, the density drops. The darkinos become less packed and act like a standard gas of dark matter particles, providing the gravity that holds the outer galaxy together. It is a single continuous fluid of dark matter that explains both the monster in the middle and the rotation of the spiral arms. It is elegant, requiring fewer moving parts than the standard model. But in astrophysics, data is king. How does the Fermionic Heart stand up against the observations that supposedly proved the black hole? Let's look at the orbit of S2 again. The Arguelles team ran simulations of the star S2 orbiting a fermionic core instead of a black hole. The result was a perfect fit. Because the core is so compact, smaller than the closest approach of S2, the gravity outside the core feels exactly the same as if it were a black hole. S2 does not know the difference because it never dives inside the fluff. Then there is the survival of G2. This is where the fermionic model wins. If Sagittarius A star is a ball of dark matter, it does not have a sharp event horizon or a singularity. As the G2 cloud passed close by, it experienced a smoother gravitational potential. It was not spaghettified because the tidal forces of a distributed core are weaker than those of a singularity. The fuzzy nature of the darkino ball allowed G2 to pass through the outer layers and survive, exactly as observed. But what about the shadow imaged by the Event Horizon Telescope? A shadow requires light to be trapped or absorbed. A black hole does this by letting light fall in and never come out. Can a ball of dark matter create a shadow? Surprisingly, yes. The core is so dense that its gravity bends light strictly. While it does not have an event horizon, the photon sphere, the region where gravity is so strong light orbits in circles, can still exist or be mimicked. The team showed that for certain ranges of darkino masses, the fermionic core is compact enough to bend light into a ring that looks indistinguishable from the image we have. However, there is a catch. A black hole should have a photon ring, an infinitely sharp subring of light. A dark matter core would not produce this infinite sharpness. Current telescopes are not yet sharp enough to tell the difference. This hypothesis also provides a fascinating answer to why other galaxies, like M87, definitely seem to have black holes while ours might not. It comes down to the critical mass. Just as a white dwarf star will collapse into a neutron star if it gets too heavy, exceeding the Chandrasekhar limit, a fermionic dark matter core has a limit. If the core accretes too much mass from eating gas, stars, or merging with other dark matter clumps, the quantum pressure can no longer withstand the gravity. When a fermionic core exceeds this critical mass, calculated to be around 100 million solar masses for certain darkino models, it collapses catastrophically. It implodes and becomes a true supermassive black hole. This implies a magnificent life cycle for galaxies. Young galaxies form around a stable fermionic core. These cores are seeds that help the galaxy grow. They can be very massive very early, solving the timing problem of early universe quasars. As the galaxy grows, the core feeds. If the galaxy gets massive enough, like the giant M87, the core collapses into a true supermassive black hole. But quiet spirals like the Milky Way might be in a Goldilocks zone. Heavy enough to have a dense core, but light enough that the core has not collapsed yet. This theory suggests that Sagittarius A star is a black hole in waiting. It is a pre-collapse object, teetering on the edge of becoming a singularity. Of course, scientific rigor demands we look at the flaws. The Fermionic Heart hypothesis is controversial, and the mainstream community remains skeptical for several reasons. Critics argue that introducing a new particle with a specific mass feels like fine-tuning. There are also particle physics constraints. If darkinos are sterile neutrinos, they should decay occasionally, releasing X-rays. Telescopes like NuSTAR and Chandra have searched for these specific X-ray signals and have found conflicting or negative results. Additionally, recent reanalyses of EHT data suggest Sagittarius A star might be slightly elongated and rotating rapidly, which is hard for a solid ball of dark matter to replicate. Furthermore, black holes usually drive relativistic jets, massive beams of energy. M87 has a huge one, but our galaxy does not. The fermionic model explains this lack of a jet because there is no singularity to drive it. However, if we find a faint jet in the Milky Way, the dark matter core theory would have a hard time explaining how a ball of fermions accelerates particles to near light speed. We are currently in a standoff. The data is blurry enough to allow both the black hole and the fermionic heart to exist as valid theories. But the fog is clearing. Two upcoming instruments will decide the winner. First, Gravity Plus, using the VLT interferometer, will track stars even closer than S2. If we find a star that orbits inside the proposed radius of the dark matter ball, its orbit will change. Inside the ball, gravity gets weaker as you go deeper, because there is less mass pulling you in. Around a black hole, gravity gets stronger forever. If we see a star's orbit relax near the center, the black hole theory is dead. Second, the next generation Event Horizon telescope will hunt for the photon ring. If Sagittarius A star has a sharp, thin photon ring, it is a black hole. If the shadow is fuzzy and lacks the ring, it is a fermionic heart. Whether Sagittarius A star is a hole in spacetime or a ball of ghost particles, the implications are profound. If it is a black hole, it confirms Einstein's general relativity to the breaking point. If it is a fermionic heart, it means dark matter is not just a background glue, but a substance that can form stars and cores. It means the center of our galaxy is a laboratory for physics beyond the standard model. It means that the monsters of the universe are actually its hearts, dense, stabilizing anchors that only die when they become too heavy to bear their own weight. For now, we watch the stars dance. We watch S2 swing by, and we wonder, is it circling a drain into infinity, or is it skimming the surface of a vast, invisible ocean? The answer lies in the dark, waiting for us to sharpen our eyes.